We're going to calculate fugacities for mixtures by using an equation of state. In particular, we'll use the Peng-Robertson equation spreadsheet from the Elliott and Lira textbook. And we're going to calculate fugacities and fugacity coefficients. So given pressure, given temperature, and given the mole fractions in the phase, we can calculate the fugacities. We'll do in this screencast just the calculation of fugacities and fugacity coefficients and show how to use the spreadsheet. And then in a subsequent screencast, we'll show how to calculate vapor-liquid equilibrium using the spreadsheet for both the liquid phase and the vapor phase. In this particular example, we'll do the calculation for the liquid phase. So here we're looking at the spreadsheet, and first let me point out I've made some changes. I went into review and unprotected the spreadsheet so I could highlight. For example, you'll see in green some of the things we're interested in. And then I also reduced the number of significant figures just to make it a little easier to see and understand what we're talking about. So in this column, Zi means mole fractions, could be either liquid or vapor. We happen to be looking at a liquid, so we've put in the mole fractions of the three components. And then I copy the critical values for benzene, isobutanol, and cyclopentane. And these I could obtain, or I did obtain, from the Peng-Robertson equation of state spreadsheet, also one of the spreadsheets that's available from the Elliott and Lira textbook website. And so I could go into that spreadsheet and copy and then paste these values here. At 315 Kelvin, and I have a pressure of 0.5 megapascals. I could certainly make this lower and still be in the liquid phase, and we'll look at that. And so we're interested in liquid phase fugacities. So let me highlight the liquid region, and then let's talk about that. So liquid here, one way you know this is the liquid, of course, it has the much smaller volume per mole. It's the stable phase because the fugacity of the mixture is lower. This fugacity in megapascals, and it's much lower in the liquid phase than the vapor phase. And then here are the three fugacity coefficients. And that's just, remember, the fugacity divided by the pressure. Here are their fugacities at these conditions. And if I were to lower the pressure, if I make this 0.05, well, first thing to notice, I'm still in the liquid phase because the fugacity of the mixture is lower in the liquid phase than it is here in the vapor phase. Here are the fugacities. Now, the fugacity coefficients change quite a bit because they're the fugacities divided by the pressure, and I changed the pressure a factor of 10. Perhaps didn't notice the fugacities did not change very much. So let's look at fugacity for benzene, 0.0054. If I change the pressure back to 0.5, increase the factor 10, this is 0.0055 megapascals. So liquid phase fugacity is very insensitive, even if I went to 5 megapascals. Well, now we're in the 1 root region. So we don't talk about liquid and vapor the same way, but clearly this is a low fugacity. This is a liquid. We're above the critical pressures for the components, but not the critical temperatures. So the fugacity changed slightly for this rather large change in pressure. And let's go back and look at the idea that we can obtain fugacities from an equation of state. If I were to lower the pressure enough, let's try this. Now we're no longer in the liquid phase region. Notice the fugacity here for the vapor phase, right? The vapor phase, the one with the larger volume, is smaller than for liquid phase. So this is the stable phase now. And here are the fugacities for this 3-component mixture at this lower pressure. We can use this equation state spreadsheet to determine vapor-liquid equilibrium by creating page for liquid and another for vapor, and there's a subsequent screencast that describes how to do this.